So thank you, Paul-André, for the introduction, and thank you for inviting me to talk about Trocq here. So Trocq is a collaborative work whose initial authors are listed here. So me, Enzo, and Assia, who's here. Actually more people, and in particular students, are also contributing as I speak, I hope. Making and turning what I'm going to present into a full tactic or a set of tactics for Rocq. But before that, let me introduce the problem we're trying to tackle with this and the relation with Malinka, because I think this is particularly well suited for the kickoff meeting. So as you can read on the Malinka website, there are 3 research tracks which stand out: the mathematical and linguistic foundation, formalization of real-world vernacular mathematics into a high-level language of representation, the Goldman Challenge, and new techniques and software tools based on natural language processing to automate the formalization process. And I believe that what I'm going to present fits in the second bullet. And why that? Well, in another part of the website, you can read that the translation in the machine of semi-formal mathematics needs to go beyond the traditional view that reduces reasoning to logic and requires to understand the dynamics of the discursive linguistic process which underlines mathematics. And what I do believe is that this step is one of the steps one of the pieces of which we are trying to fulfill with Trocq, because in the end, you still need to reduce your reasoning, however fuzzy it is, to logic, because that's the only thing that a proof assistant will ever accept. And when you try to do this in the ways that proof assistants allow you to do nowadays, it often causes a lot of frustration. And I will list a number of frustrations that proof assistant users came up to me with during various events. So those frustrations, I classified them into 3 bullets. So I only kept the one that served my purpose. I think there are so many more, but let's only list those 3 kind right now. So the first is tied to what you're supposed to be able to compute, but you maybe are not exactly in the fragment that the proof assistant allows you to compute in. For example, if you run the ring tactic or linear arithmetic tactic, or if you know you can compute with such or such data structure, maybe you're slightly off and you need to do a small translation before you actually can use the capabilities of the proof assistant. So that's one. The second point is sometimes you have all the theory you want about one object, but you have an isomorphic one, and now you're lost because you don't know much, and you must manually insert isomorphisms everywhere to make it work. Or worse, if there is no isomorphism, but you know that when you go to the quotient it should work, and intuitively that's what you usually do to convince your colleagues. Well, the proof assistant won't be convinced by that. You have to find other ways. And the third point is the things that I say are created by the use of type theory. I missed the quotes, but I usually put quotes around this because type theorists will say, what do you mean created by type theory? Type theory is the right framework to do things. But people who used to set theory, they do think that those problems arise from the misuse of from the use of the wrong logical framework. But in type theory, so when you formalize things in type theory, you cannot use the inclusion from natural numbers to extended natural numbers, or from natural numbers to integers to rationals to reals, or from measurable sequences into sequences where you allow to have an infinite. Anyone who tried to tackle those problems, sometimes they rely on an ad hoc tactic to push coercions around, or they say, oh, let's just work in the biggest possible type that we are actually using. But this changes, and that's why I put which button is this? dot here, because you might say at some point, I mean, if Berthaud is developing this thing for undergraduate students, and he's taking the reals as the biggest possible type, but at some point you may want to put the complex or quaternions or any other extension of the reals, or maybe you want to fork on the other side and go to p-adic numbers, and then you don't have the proper join, at least I don't know how, which one to use. So it seems like you're stuck, and that's where I'm going to show how we can get out of this situation. So for the first example, one typical thing that it was not possible to do in MathLib and is not possible to do in MathComp, so either in Lean or Rocq, where you have you want to show that the degree of a polynomial is, for example, this polynomial is exactly 7. I mean, it's a very concrete polynomial, and you have a very concrete number as output. But at least in MathLib, the polynomials, they are non-computable. So the degree will not compute unless you change representation. And in Rocq, it's almost the same. Although it's computable, there is also a lock that is designed to make sure that the kernel will not explode, or that the reduction in the middle of a proof will not give you an unexpected new polynomial that you didn't want to see in the first place. So this is the kind of thing I was saying when I was saying that you sometimes have the wrong representation and you want to slightly shift. For the example of the second kind, I will take the example of reduction modulo, and I took the two problems that I came across in talks that I attended. The first one is an exercise for students, and you can read it in I mean, they use this example in the THEDU paper with, I can't remember the exact list of authors, but I will put it later on. And this second example, so if 3 does not divide ABC, then a to the a cubed plus b cubed is different from c cubed. It's not an exercise for students, it's actually a part of the proof for the Fermat's theorem for n equals 3, right? So, and usually you would convince your colleagues by saying, it's by reduction modulo 9, you just check the cases and you're done. But that's not what you can do nowadays in a proof assistant. You need to explain how to perform the reduction and then to tell it to compute all the cases. And the third kind of problem, I love it because there is it's a quirk of 2 libraries at least. So what, in your opinion, should be the type of the degree of a polynomial? Should it be who votes for the degree goes to n? Who votes for the degree goes to n extended with minus infinity? So at least there was not a... there were still people who voted for the second one, and I think people for the first one, and I think some people even voted for the 2. Yeah, because you are an insider. Indeed, MathLib has both, right? And you need both. Because you want to reason on natural number arithmetic whenever you can, and sometimes you can't, and you need the second one. And the mathematical components library in Rocq has neither, actually. It uses the size function, which is total, but doesn't behave well in algebraically. So it has other benefits, but other disadvantages. So you have actually 3 options. And what my claim is they should all coexist, actually, and we should bridge them. And you cannot do it easily in type theory because you don't have the inclusion that you usually have in type theory. Okay, so now let me give you an example on how Trocq, the prototype I'm going to present, actually solves the highlighted problem, reduction modulo 9. So this is a mock-up session, but still using, I mean, I still import mathematical components, but I specialized a lot of things because right now Trocq is just a prototype and it's not meant to work out of the box yet. So I had to do a few things to prepare the use, but nevertheless, you can read the statement here it's a statement on integers. So you quantify over 3 integers. Then you perform multiplications in integers. You reduce modulo 3, and you check whether it's non-zero. And here it's implicitly, because I specialized it, modulo 9. So it's different from 0. Modulo 9, that's what the triple equal means here. And if this holds, then the m cubed plus n cubed can't be equal to p cubed. So this is a disequality in the integers. So all of this is in the integer, except this does not, this is not equal to 0 modulo 9. And using the prototype, we can actually use the reduction modulo 9, and it substitutes, so this is the debug log, don't read it. And you can actually see that it changed the quantification on integers to a quantification on z modulo 9. And this becomes an equality now, so a disequality. This is still modulo 3. And this is still an equality, but this time of integers modulo 9, which means you can do, you can explore all the 9 to the 3, 9 cubed cases, and in the end, you have a full proof. It takes, we could have cut down the number of cases to explore, but that's not the point of the talk. So in the end, you have a full proof which has no assumption. So I'm just proving to you that even though it's a mock-up session, it still does not use any axiom, since Rocq tells me it's closed under the global context. Okay. Don't hesitate to ask questions. Who's speaking?
This theorem. Who has proved it for the first time?
No.
Sophie Germain.
Okay.
It is true for any prime of Sophie Germain.
Okay.
So,
thank you. Okay, let's move on. In my dream world of future Rocq tactics, you thus have a way to solve the first problem by using a decide. So I named it decide after, it's the name of the equivalent lean tactic, but which proceeds in another way. This decide tactic will actually use everything that it knows about how to compute things in your library and then run the computation, for example, using one of the computation engines of Rocq. For example, ultimately, I wish that the example I showed you uses mod 9, which is actually a function, infers that this function, the graph of this function is actually a relation, that this function is an epimorphism, and use this knowledge to actually perform exactly the things I showed you before, and then conclude, instead of doing a manual case exploration, conclude with the same decide tactic I showed above that does not exist yet, but which translates all for all on bounded quantification into a list of cases to explore and actually run the algorithm that's written underneath, but maybe in an optimized version instead of a naive version. And then for the problems created by type theory, actually, if you know, if you're reasoning on extended natural numbers and you know some of them are finite, well, you might as well use the fact that they're finite, so make the system infer it, and then translate your whole goal into a normal arithmetic question on natural numbers instead of the extended ones.
Cyril, maybe I misunderstood the first example. I just checked that Mahboubi has no issue computing.
Yeah, it's changed, I think, in order to last years. Even multivariate polynomials.
This I don't know.
no.
Because so
you're using compute degree.
yeah. So
We have a tactic.
tactic that does that. So, but it's a specific tactic for so the difference is this is meant to be a generic tactic rather than a tactic that computes just the degree.
No, and it's called compute degree, but you cannot compute anything. You have to know the degree in advance and
okay.
prove that the degree is 7.
Okay.
This was what was written.
Yes, so there is a compute degree tactic in Mathlib that checks that the degree is a given number. But this is meant to be more general than that because it's meant to be used to compute anything that you know how to compute in your library. And maybe you don't know the result in advance, and then you get the result and not just check the result. Okay. All these problems, for me, they boil down to problems that I used to have a few years ago. I mean, more than 10 years ago. And at some point during my PhD studies, I had this simple matrix, and I couldn't even get the determinant, and this was frustrating because all the computation was locked, and I wanted to unlock. So this is an instance of the first problem, actually. The same can occur with a primality test, where the computation will take more than 2 minutes, which is way longer than you want to wait for such a small number. But since in Rocq, as it is right now, it's using this particular algorithm is using unary natural numbers. It will, it's unreasonable to do this. And another problem that you might have is that you want to reason on an equivalent type. So this is a very dumb problem just to illustrate my speech. But if you want to prove that for all booleans x XOR x is false, maybe you already have the result in your library on z modulo 2, and you want to apply it, but you need to transport everything through the isomorphism. But those problems, they seem distant from the one I just solved before with reduction modulo 9. But the thing is, they have the same, the solutions that were found to this problem have the same root. So the solutions that were found were those two at the time. So one was doing only data transfer, and the other one was using change of representation via isomorphism using the univalence axiom. And Trocq is actually generalizing both, because we may be able not to use the univalence axiom and deal with only partial isomorphisms if you only have this at your disposal. So the main idea of all those techniques is to exploit the underlying structural properties of the logical framework. Here, the type theory, the dependent type theory of both Rocq, Lin, Agda, whatever dependent type theory you have. So Trocq right now, so this is the one of the reasons why we call it Trocq. The other reason is that it's transfer for Rocq. And it's described in a paper. Actually, there is another paper now, but it's essentially a calculus that is based on a parametricity translation. It has a LP implementation of the calculus and a prototype tactic that tests that it actually does what we want to do. So that's what I demonstrated just before. Okay, so let's illustrate how Trocq works on the very much canonical example of the change of representation between natural numbers. So this is, I think, the first paper in proof transfer by Nicolas Magot in Rocq was actually using this example, and everyone's been using it since then. So imagine you have two representations. The first one is the one that you have in Rocq when you do nothing and you just write nat. It's the unary natural numbers, because you have either 0 or successor, where you add just one. And this gives a very natural induction principle, which is the one that you want to see about natural numbers, the recursion, the induction of natural numbers. If you want to prove something for a property over n, you test it in 0, and then you test that if it's true for n, it's true for a successor of n. But then you may want to have more efficient representations for computation. So among all the representations, one of the most naive and natural one for computing is the binary one, where this time, instead of having a unary, you have at least 2 digits, and you can do you can compress exponentially your numbers. So you have the constructor which puts the digit 1, the constructor which puts the digit 0, and the end of stream digit. So essentially, you should only look at those two, and this one is end. And then natural numbers are either 0 or a sequence of digits, and the end is actually a 1. And then you can reprogram the successor for positives, and then the successor for this binary representation. But now, you don't have the same data type, so you don't have the same natural induction principle, and you may want to avoid duplicating work. So what you can notice is that there is a bijection between the two, which is quite easy to write down and prove. And you also know that the successor and 0 are related through this isomorphism. So nothing surprising so far. But you may want then to transport some properties. For example, the associativity. Why is it written comme? The associativity. Never mind. The associativity of addition, you might want to get it by transport rather than reproving it from scratch. The induction principle you had before, which is not the natural induction principle for the binary representation, maybe you want to reuse the one that you have since it's for free. Or maybe you want to compute over natural numbers, but maybe you don't want to use unary representation for performance, and you want to first do the computation on the binary representation, and then get your result back by translating it. Okay, and many more things that you may want to do. So, okay, so how does parametricity help us fulfilling this job? Well, let's start with this equation that is satisfied. I mean, you need to prove it first, but let's try to rephrase it in terms of logical relation. So first, you can introduce the fact you can uncontract the statement. I don't know how to say it otherwise. You can take out this member and put it here so that you have the same shape here and there that you can abstract as a relation. So this relation is two terms are in relation if they are in correspondence via the isomorphism. And then you can introduce the relation that corresponds to the implication, which says the implication of two relations relates two functions if for all related arguments they are mapped to related outputs. And this statement can be rephrased that way. So those two are equivalent. And actually, this kind of rephrasing is way more general. Every construction has a translation, so I will write double bracket the translation. And so this is the translation of the implication. So this S, which goes from natural numbers to natural numbers, is turned into a relation between the two kinds of natural numbers. For pairs, it works the same. So if you have a pair, if you want to show a pair is two pairs are related, the first component must be related and the second component should be related. For lists, well, the translation of the list constructor is a relation which relates lists that must have the same size and which elements are pairwise related, and so on and so forth. So, and then you naturally land in the land of parametricity, and it generalizes to the whole calculus of construction as shown by Bernardi and Lasson in 2011, where you have a translation for, so this is the generalization of the arrow. So for the pi type, it's essentially exactly the same. So if two inputs are related, then their outputs are related. But then you also have it for the lambda, for the application, for variables, because you put them in your context, and for the universe, which becomes a relation, an arbitrary relation. How does that help us? Well, there is an abstraction theorem that tells us that whichever term you take, so forget about the context, so whichever term you take, the translation of a term is a proof that the relation arising from its type relates the term with its potential translation. Okay. We can rephrase this into a slightly different shape that I will try to explain briefly. So instead of writing double brackets like this, you put the translation as the third component of this ternary relation. So for example, in the case of the translation of the product, you can see that two products are related, and the witness of this relation is the fact that if you have XR, which means that X and X prime are related by AR, then f of X and G of X prime are related. So this is a rephrasing that will be very useful later. And the abstraction theorem can be re-expressed as if two terms A and A prime, no, sorry, M and M prime are related by MR, then MR is a witness that M and M prime are related by the relation arising from the type of M. Okay. Bear with me 5 more minutes. Now, how does this apply to one of our initial problems? We wanted to use this equality to compute with unary natural numbers using binary natural numbers. How are we going to do that? Well, let's re-express, just for the purpose of being very down to earth, this sum as a fold. So fold takes first element, an operation, and it iterates the operation using all the elements of the list you provide. If I manage to get a witness W that those two are related, then I win. Why do I win? Because in order to do this, I first need to assume that I have a function phi that happens to be an isomorphism, but maybe I don't have to know it's an isomorphism. Then I need to know that n and the binary version of natural numbers and the unary version are related, and the witness of relation is the fact that phi of m is equal to n. Then I need to know that the zeros are related, and the witness of this relation is a proof that phi of 0 equals 0, which I know how to do. I need the same for successor. And what is the same for successor? It's a proof that I can do that if phi of m equals n, then phi of successor of m is equal to successor of n in the other data type. So that's what I showed you. I rephrased the commutation property earlier. You need to know the same for the plus. And then you're done magically, because by the abstraction theorem, the type of W is the relation between those two, which means that phi of this equals this. If I replace phi with, phi is just another notation. I should have identified the two, but phi is just the transfer from one type from one type to the other. Or maybe it's the other way around, but it doesn't matter. In the end, I get this equality. I get for free by just running my translation that W is a proof that those two coincide, whatever I put in there. So this is why parametricity is a super nice solution to solve this problem. However, it's not good enough to solve the other problems I mentioned, to transfer property via isomorphism, because if now I take a property instead of a computation on numbers, then I get a witness. The type of this witness is the translation of the type of the return type of my property, which is the translation of type. The translation of type is an arbitrary relation. Hence, W has type any relation between those two properties, which gives me absolutely nothing. So the idea that Mathieu Sozo, Nicolas Tabarot, and Eric Tanter had was to actually change the translation and make it so that we have here an equivalence. And this led to univalent parametricity. So univalent parametricity is the same as parametricity, except that instead of translating type with an arbitrary relation, you translate it into something more complex. You translate it into a triple, which first component is a relation, but not any relation. It must be a relation, an equivalence, and a proof that this relation is the same as the graph of the equivalence, which essentially means that it says this relation is an equivalence relation. So it specializes normal parametricity, which used to translate types with arbitrary relation to translating types to equivalence relations. And the surprising thing is that you can actually write the whole translation and the abstraction theorem still holds. But now it's stronger. Because when the abstraction theorem holds for type, it means that not only A and A prime are related by any relation, it means they are equivalent this time. Which is exactly what we wanted before. Okay. It also means that in order to prove this translation, to make this translation and then prove it correct, you need here to input the I think it's, if it's not literally the univalence axiom, it's a variation of it. So you need the univalence axiom to make this work. So that's the catch of this approach. You need to be in a univalent setting. So you need to, for those who don't maybe know what is a univalence, it essentially says that equality is equivalent to equivalence. I mean, that's a consequence, but it's not the whole picture, but you need at least that. Okay, so from this we can do calculus exactly as before by replacing the third component, which used to be a simple relation in many cases, by equivalences now. But that's maybe not that important. The only thing you need to remember is it works almost the same, except sometimes you need to project out of your third component. So P here, MR is the third, AR is the third component, which is not directly a relation, but it's a relation plus a proof that it's an equivalence relation. So you need to project to get a relation. So it's almost the same, but it's the same pattern. The calculus look the same. You just have to put some first projections here and there, and it works. The proofs are not so trivial, but I mean, the proof of the abstraction theorem, you need to do some work in some cases, and not only for univalence. Okay, so now let's observe this equivalence, this type of equivalence relations I mentioned before, and make some observations about this. So first, in order to inhabit it for type, it triggers the need for univalence. It's equivalent. Inhabiting it for type is equivalent. I'm not sure it's equivalent, but I don't know how to do it without univalence, and it's certainly very close to univalence. And also, it's not symmetric, because here you make a choice you pick an equivalence. An equivalence is a function with a proof of that this function is an equivalence, which means E is directed in some way. It's not symmetric in A and B. And this corresponds actually to the way we generalize. We take out univalence and we make it work with partial ISO by cutting this, by changing this notion to a different one and cutting it into pieces. So the pieces we cut it into are the following. So first, we use a variation of an exercise in the hotbook to rephrase equivalence in the following way. A and B are equivalent, This time not if there is a function that is an equivalence, but if there is a relation that is functional both ways, with a very strong meaning for functional, which is not only the existence of a function, but the contractibility of the fibers of the relation. So it's a very strong notion of being a function for a relation. So isfn of R is for all A, there is a unique element, there is one and it's unique element in sigma B RAB. If you want to read it more naively, there is a B such that RAB, but there's more than that. And we write R minus 1 the symmetric of this relation, and this gives you the full phrasing of this notion of equivalence. But that's not the end of the story. Then we cut isfn into pieces. So this is a variation of rephrasing by Altenkirch and Kaposi, but with a twist. So we changed, so isfn was this thing, and we defined isumap as a sigma type with 4 components. And the 3 first components are quite easy to understand. The 4th one, where the twist is I will leave it for later. So the first component tells you there is a function. The second component tells you that the graph of this function is included in the relation, but the relation is not proof irrelevant. So take this inclusion as with caution. Then the third component tells you the relation is included in the graph of the function, and the fourth component tells you that there is some coherence which is necessary to make it equivalent to being a function, but let's forget about it. And now, with this rephrasing, we define the translation of the universe, which I call double box since the beginning. But we define, let's say, double box top, and you will see why I call it double box top, as sigma R followed by those 2 components I just described. So how does that help us? Well, we are going to cut it into several pieces because we are going to make a lattice of relations between the 2 types. So this lattice of relations is classified by alpha. So alpha is a pair of 5 possible annotations, and according to the number I put, I will have more or less pieces of the decomposition I showed before. So more precisely, this relation on the universe I'm constructing parameterized on alpha is a relation, so it takes 2 types A and B, and it's defined as a relation which has class alpha of R as its property, and then class alpha is the combination of 2 potentially 2 different requirements on the 2 sides of the relation. So let's take one side, for example, from left to right side of the relation. If I say n equals 0, it means I have nothing. So 0, 0, which is the bottom of my lattice. Maybe I can show the lattice right away. So 0, 0 corresponds to just a relation because I'm packaging a relation with nothing and nothing. Right? So it's just a relation, sigma R unit. Then I can add, if I put 1 in n and 0 in k, then I have just one function from A to B. If I have 1 and 1, then I have 2 functions, one from A to B, one from B to A. If I add more, I can add the fact that the relation, that the graph of the function is included in the relation. I can put it on one side, on the other side, on both sides, on neither, and so on and so forth. So I had 6 different, I said 5, it's 6 different annotations for both sides, so 36 possibilities. So this corresponds to the product of those 2 lattices. So I have a 36-element lattice, which is the product of those two, where at the bottom I have, as I just said, just a relation, and at the top, that's why I called in my previous slides double box top, it's equivalent to an equivalence, so we get back univalent parametricity. But we have 34 more levels, which correspond to various things. And among those, some of them have meanings we know, and some of them have strange meanings and are just artifacts of computation. For example, so we saw bottom, we saw top, and then we have 4, 0. So 4, 0 is functional on one side and nothing on the other side. So it's just a function. But it's a function that has exactly the same graph as the relation. That's the difference between 1, 0 and 4, 0. 1, 0 is a function that is unrelated to my relation. I just know I can go from one to the other. But 4, 0 means that my relation is exactly a function. 0, 4 is exactly a function in the other direction. Then 4 to A is actually the same as is exactly the same as a split surjection. Meaning I have a function, since I have 4 on the left-hand side, my relation is functional, but since I have 2A on the other side, it means I also have a function on the other side, and the characterization that I have on this function makes the other function from A to B surjective. And if I put 2B, I get the same, except it makes the function from A to B injective, but with an explicit left or right inverse, depending on the case. So those 6 levels have a very clear meaning. All the others are strange. Well, you can also flip those two, and then you have a very clear meaning. But anyway. Then, maybe I skipped this one, but yes, I skipped this one. So this is maybe too complex of a question for 5 minutes. So the thing is, in the end, okay, I will show you, but you really don't need to read it in full. But this is the calculus we get in the end. So this is the Trocq calculus, where you need to, instead of a triple, you have 4 components. For example, let's take the pi. So the pi x of A and B, pi x of type A, B is related to pi x prime, A prime of type B prime, as before. But we need to specify at which level, since we have a variety of levels, we need to tell it whether it's rather the raw parametricity which will just give a relation, or whether we want more out of it, in which case we put top, for example. And it will give us the associated elements. Maybe something I should say about this, and I forgot to write, but it's very important, is how can we use this for goal translation? Well, if I have a goal G to prove, so I have my hypothesis and I have G to prove, how should I reduce G to G prime? Well, I need to find an implication from G to G prime in order to apply it to, so I need to apply this to my goal to get the result. And what is such a thing? Well, an arrow, so if I see it in a substitution way, I need to substitute G with G prime using this. So what I need is actually this. Right? Because this is equivalent to G prime implies G. And this is exactly what I need. So I can initialize my calculus with, please Trocq, given G, and my context, so my context, given G, give me a witness of translation at level 0, 1. Then Trocq computes G prime, and a witness W, and W has type G prime implies G. That's what happens using this calculus. And then I can just apply W, and I perform my translation. And the funny thing is, from 0, 1, which is the entry point for substitution, I mean, you can imagine other applications of Trocq, but for substitution, the entry point is 0, 1. But through all the constructions, it may propagate in a way where you require 0 to A somewhere, 4, 0 somewhere else, and so on. And for example, when you go through a pi, you see that if you want delta as an output, you need to provide alpha and beta as input following a certain table of relations that okay, so this is the detail of the pi rule. So in order to get delta, you need to require alpha and beta on the inputs, which means that you can build the table of all the requirements you may have. So given delta, given 0, 1, what do I need on the input and output? And since this is very symmetric, the table is very simple to write down. These are the tables. So how to read this one? If I want to get a level 1 on my output, I need to provide a level 1 on the conclusion of the pi, on the B, and on the A, I need a 2A. If it was just a non-dependent product, I would only require a 1, which is very natural. Maybe the most natural case is the 4, because then you can simplify everything, imagine a relation, and the last line on the left simply means that in order to get an implication between two pi's, I need an implication between A prime and from A prime to A, and in a context where well, I put everything I need in my context, I need an implication from B to B prime. So the fourth line just means this. But then what Trocq does is it generalizes this to not only implication, but an arbitrary relation from our lattice here. So here, gamma, alpha, and beta with the table that tells us the requirements of the pi. And these are tight, thanks, and the proof is from Lucilla, who contributed a lot to Trocq in the past months. Okay.
What do you mean by optimal?
Optimal in the sense that given the lattice, there is you cannot weaken any of those levels. You cannot find a weaker condition to require for all the rules that for all the pi and implication rules. Okay. Okay. So in Trocq we can change represent. I forgot about the no univalence. It was in the slides that I skipped, but what you need to, okay. In the current version, in the current version, meaning with the current lattice, univalence is required if and only if at some point you ask for a translation of type alpha such that alpha is greater than the 2b0 or 0-b in the lattice. And this does not happen as many times as you can think. I mean, we have a lot of examples where this does not happen, and you don't need univalence at all to perform the translation. So this is what I explained. In order to reduce a goal G to an hypothesis H, so H is my G prime, then depending on the occurrences of what you want to substitute in the goal and in H, the invariant might be kept, and you may need, if you don't need more than partial isomorphisms, then it will just compute with what is it you have, and in particular, in the case of reduction modulo 9, you just need a function from one to the other. In the example of when you translate an induction principle to another one, you need a split surjection, for example. So you can show the induction principle for natural number holds for a weaker structure than natural numbers. Of course, it can hold for integers modulo, for example, and it doesn't need to be all natural numbers. Okay, so what's next? Well, we could use Trocq to generalize rewriting, so going further than my dream tactic. So given a goal and a set of relations, you may want to abstract in your goal a common pattern P and then perform a substitution. So it amounts again to finding a 0-1 translation of your pattern, and then using the relation, you can just plug them in your relation, and it will perform rewriting across different types, abstracting only the occurrences you need. So right now the prototype is blind, and it tries to translate every occurrence by first selecting a pattern that is that you can type check. Then you ensure that you can select only the occurrences that you really want to translate and not all occurrences. For example, if you're translating a matrix of natural numbers, you don't want to translate the indices, you want to translate the contents. So this kind of technique will make it possible not to be too brutal when translating. And I think it's the end. Oh, no, we can imagine more. Instead of having to translate manually statements, we can imagine to use Trocq to boost unification. So for example, instead of confronted with this problem, which doesn't type check, well, you can reinterpret the equality as which relation would actually make it type check, and what is the solution for the undeterminates. So for example, here the solution would be, well, x and y are natural number, I coerce them to z, then I reinterpret the equality as the relation which puts in correspondence n and z, and I just need to find in my context or using type classes or whatever, proofs of morphisms of this coercion to make it completely work. For example, if I want, this is forget about carriers, just if I want to find a ring which is in some relation with z, then the solution would be to pick the ring associated to z, to pick the equality as being the coercion, the application of the coercion from z to type, so the forgetful functor from ring to type, to the first element, and it would put the two in correspondence. And if I want to identify natural numbers to extended natural numbers, then I can say, if I find a proof of finiteness of n, then I can just pick x to be the finite number associated to n, potentially throwing away minus infinity and putting it to 0, but it doesn't matter. And the equality here is in fact the graph of the coercion from n to extended numbers. Yeah, I'm done.
Okay, thank you, Cyril. Great talk. So, are there questions or comments? Yes. Okay. Sarah.
First, thank you for your talk. It is absolutely fantastic.
Thank you.
Then I kind of recognize in the lattices you described more finer granularity to what is done with usually directed type theories. Mm-hmm. And my question would be, why you need this granularity? Why at some point you need, for instance, a split AP?
Okay. Well, the only answer I have is experimentally, in order to do some translations, you land exactly on this level and you don't need more. And that's the case, for example, for the induction on natural numbers. If you want to translate it from one to the other, if it's from n to binary n, then you have an ISO, so you don't care, right? But if you had less structure on your relation, it would still work with a split epi. And there are some, I don't know all the situations where it can occur, but there are some situations where you actually need more than a function, but less than an ISO. And these are the situations where you would need something finer.
Thank you.
Yes, of course. Are there other questions? Or okay, so there is a question. No. So okay. Yes, I think we have questions. It's just a matter of.
So thanks for the talk. So I had the impression that you used a lot the fact that n is defined as an inductive type. So does this work for example, if I have a theorem about the real numbers defined about the Cauchy reals, and I want to check if the same theorem applies for Dedekind cats or whatever? Yeah. Does it work to do this?
I hope it does. I mean. Okay.
I want in principle, it should work.
That's one of the.
My question is, that should in principle work? Yeah.
In principle, it should work, and I mean, Lucy tried to work on it for a few days, but in a few days it was not possible to do it. But it's definitely one of the next targets. We want to apply it to models of the reals, to models of the p-adic numbers, to various situations where you want to do. And nothing I said in this talk is tied to inductive types. We need a generic translation for inductive types and its ongoing work in order to make the calculus scale to the calculus of inductive construction in full. We have many examples of inductive types where we did the translations manually without any problem for all the levels, and we have tables akin to the ones for pi, but for other inductive types. But for the translation itself, between isomorphic objects, the relation need not be between inductive types.
So maybe a slightly more technical question. So you phrased the whole kind of parametricity is phrased using relations. Using relations,
yes.
But then all of the kind of practical examples that you start with are all phrased in terms of like having an actual coercion function one way or another. And so I guess the question was, is the phrasing in terms of relation mostly because that's the right way to think about the parametricity relation without going crazy? Or do you have interesting examples where you naturally want to express the relation really as a relation in some base cases?
In the base cases, I don't know an example where it's not the graph of a function. But in the intermediate steps, it occurs, right? As soon as you take a function space, if you didn't have the right variance, then here it's the example I gave was with the right variance, but as soon as you weaken a little bit, you don't have the graph of a function anymore.
Okay, so the whole relation view is more to make the parametricity translation work than to actually install the example.
Yeah, in the inductive case, you lose this property, but you keep the fact that it's a relation, and it may have some levels.
Right, thanks.
So any other question? Or okay. So Philippe.
Okay, thank you very much for your talk. Okay, since this is like the last day, I allow me a sort of intuitive and informal question. But first of all, I want to make a remark. I think that what you call problems created by type theory are actually problems created by formalization, because in set theory, integers are equivalence classes of pairs of natural numbers, so there is no real inclusions. There is a canonical injection, but no real inclusions. But my question is the following. One can see a relation, like a logical relation, like the composition of a morphism and an inverse morphism, like a span. And I'm thinking of that because of what Paul-André is calling the art of looking at things from above. And could we see those relations like that from I do not know which category, getting a sort of better way of abstract view of both point of view?
Probably. You mean generalizing this to maybe more than relations spans in another category? Because here it's relation it spans in the category of types, right? Well, I don't know. Maybe there is a. I don't know. The answer is I don't know. It's an interesting thing to consider, though.
Yes. So I mean, maybe.
But I agree that created by type theory is a bit of a lie. Sorry?
Sometimes it's really because of type theory. For example, the positive real numbers that are not real numbers, this is really type theory, it's not math.
Type, yeah, this is real, yeah. I agree.
Maybe just to carry on with Philippe's remark. So there are two elements. So one is about refinements. So for instance, when we look at programming languages, because there are like kind of maybe. So some of the inclusions could be seen as some kind of effect, so then there are techniques to show that the programs or the proofs are indeed like not effects, they are values.
Yep.
So for instance, that the natural number is a natural number. So it's a little bit like the question by Philip. So is there a way to, are there some kind of proof techniques coming? We could imagine coming from programming language semantics that would say, okay, this generalized natural number, which could be infinite, in fact, is a natural number. Yes, that's one question.
Here, so in this particular line of work, you would say, since I can infer it's actually finite, I can perform a transfer and remove the effect.
Yes, exactly.
This is about the removal of the effect, rather than computing that it's actually a value.
Yes.
But the two sides should be combined indeed. When I say with the proof of finiteness here, the proof of finiteness is usually the result, or would usually be the result of an inference that might be arbitrarily complicated or completely structural, actually.
Yes. And if you go even, into some kind of concepts, like the kind of hierarchy of concepts that you have like in MacComp and MATLib. So very often, for instance, in mathematics, you know that something is a monoid, and then you want to show that it's a group.
Yep.
So it's a little bit like you know that it's a completed natural number, and then you show that it's.
Yep.
So there is some kind of a lot of the proofs we do are about refining.
Yep.
And I think you would have something a little bit. How we climb the stairs of the concept. So, we move from, like, it's a very common situation.
Yes. How would you apply Trocq to this?
There should be some kind of, in mathematics very often you prove something like it's in B, and you know that A is included in B, so groups are included in,
yes.
And you work against the, like the salmon goes against the, the flow and gets back to A, and I feel like there should be something.
Yes. Probably this is illustrated by the first or the second example, actually, yes. Where you could boost the unification with Trocq to generalize, but you also need to not consider things up to conversion anymore.
Yes. And maybe again, sorry, I'm a bit long, but something that we could imagine is that instead of having relation, we would have like categorified relations. That was the idea of a span. Yes. so that, for instance, a proof that has been done in one representation of the real, so here it says, okay, there is another proof, and we can move from one to the other.
Yeah.
But we could imagine that we translate it, in some way, that there is some kind of, and I think this is something you have in mind, yes?
Yes.
So and then we could, especially with this morning's talk, we could write a proof, for instance, in some synthetic, analysis where with, epsilons, but as first class, elements, and then turn it into epsilon delta proof. These kind of things we could. It's great that you have this parametricity. I agree. This was Sarah's. Yeah, it's fantastic. Yes, it's really good. But one could imagine that even at the level of translations between representations. And I think. But anyway, this will be based on your work and in some ways. Yes. So it's really cool. Are there other questions or comments? Sorry, I became the talking chair. Yes. So. Okay, so thank you, Cyril. Yeah. Thank you.